In this video, we're going to be talking about Simpson's rule. This is going to build on the trapezoidal rule that we saw in the previous video. So the idea is the same kind of setup as we saw in the previous video. We want to approximate the value of a certain definite integral. So sometimes these integrals can be hard or impossible to compute directly, and instead we use a numerical method to just approximate the value. So what that represents geometrically is the area under the curve, y equal f of x, between two specific x values. So I'm going to write down Simpson's rule, and then we'll draw a picture or two just to figure out where that rule is coming from. So here's the statement of Simpson's rule. You might remember from the trapezoidal rule that n represents the number of intervals that we're going to use along the x-axis. So we'll draw a picture of that in a minute. In order to apply Simpson's rule, n must be an even number. So Simpson's rule only works when n is 2, 4, 6, etc. It does not work when n is odd, and we'll draw a picture just to indicate why that's the case. So the actual rule says that to approximate a definite integral, you're going to take b minus a, divide by 3n, and multiply that by some specific y values. So the y values represent the height of the curve at a few different points along the x-axis. Now, probably what's most interesting here is just the pattern of the coefficients that we're seeing in this bracket. The pattern is that the first and last y values that you put in here have coefficient 1, and then in the middle, the coefficients alternate 4, 2, 4, 2, etc. So 4, 2, 4, 2, all the way across here. Because you've got an even number of intervals, you'll actually have an odd number of y values. Therefore, the second last y value will always be a 4. The second last coefficient will always be a 4. So the pattern is coefficient 1 on the outside, and then on the inside, coefficients alternate 4, 2, 4, 2, 4, etc. So for now, let's draw a picture and just understand where Simpson's rule is coming from. Make sure we understand the b, the a, the n, and the y values. So we've got this curve, y equal f of x, and we've got a certain portion of the x-axis which we're interested in. So our x values are ranging from a to b, and we're trying to find the area under the curve. A represents a small number on the integral, b represents the big number on the integral, and n represents your number of intervals. Now, we were told that n must be even in Simpson's rule. So the idea is that we're going to break this interval from a to b up into n parts. Could be something like 4 or 6 parts. But we're going to break it up into an even number of parts. And the reason is that we're going to pair up these little intervals. So we're going to pair up these two areas. We're going to pair up these two areas. And similarly all the way across. So all these little areas are getting paired up. So that's why we need n to be even, so that that pairing can work perfectly. Now, the geometry behind what Simpson's rule actually does is it looks at these intervals, or these areas here, 2 at a time. It looks at the 3 points that lie on our curve, and it finds the parabola through those points. So it's the same thing for every pair of areas. So over here, there would be some parabola, maybe looking like that passes through those points. So this gives a slightly better approximation to the area, because we're then going to calculate the total area under the curve by saying, well, let's figure out the area under the parabola just over this section of the x-axis. So that's one calculation. And then separately, we look at the area under the parabola over that part of the x-axis, and then we sum up those areas. So this gives typically a better approximation than the trapezoidal rule. But it does have the restriction that n has to be even so that you can pair up the intervals. So I want to give you a little bit of insight here as to how this picture that we've drawn connects with the Simpson's rule formula. We're trying to approximate the value of an integral like this. We'll say it's approximately the total area under these parabolas. So if your number of intervals were 4, for example, you'd have 2 parabolas. If your number of intervals were 10, you'd have 5 parabolas, for example. And let's just look at maybe the one on the left here. and figure out what that area might look like. So the length of the step that we're taking along the x-axis is b minus a over n. But if you're pairing up these intervals, you're actually getting double that. So it's actually 2 times b minus a over n. And then essentially what Simpson's rule does is it finds a way of taking a weighted average of the heights. So instead of just taking the 3 heights here and doing a pure average where you add them up and divide by 3, it actually does a weighted average so that it's weighting the middle one a little bit more. So we do something like y0 plus 4y1 plus y2. And because the sum of the coefficients there is 6, we actually need to divide by 6 to make that a good weighted average. Then I'll write plus ... here because this is just the area under the first parabola, and we're going to have more parabolas like that as we work our way across the x-axis. So you can start to see where the formula is going to come from because you're going to get cancellation between the 2 and the 6 here. So that explains why we end up with a b minus a over 3n out in front. And then if we look at the pattern of the coefficients, you're going to have y0 plus 4y1 plus y2 coming from the first parabola, but then from the second parabola, you're going to have y2 plus 4y3 plus y4, etc. as we work our way across the different parabolas in that picture. And so now we can start to see where the coefficients are going to come from because that y2 is being used as the right endpoint of the first parabola, but also the left endpoint of the second parabola. So those are going to double up. And that explains where this coefficient pattern of 1 on the outside and then 4, 2, 4, 2, 4, etc. comes from on the inside, just to give you a little bit of insight as to where the formula is coming from. So as for specifically why this is the correct weighted average to use, that just has to do with the algebra behind finding the parabola through those points. So without going through too many details, we'll just say that's the correct weighted average to correspond to the geometric idea that we've got in the picture. So at this point, we've stated Simpson's rule, and we've talked a little bit about the geometry of where Simpson's rule comes from. I never like to just plop down a formula and say, here, we're going to plug into this. It's always nice to have a picture. So we have a sense here that we're using parabolas to estimate the area under that curve. So we are going to approximate the integral from 1 to 5 of the square root of 1 plus x squared using Simpson's rule with 4 intervals. We'll give our answer to 2 decimal places. Remember that your number of intervals must always be even for Simpson's rule because you're actually pairing up those intervals as you do the Simpson's rule process. So first thing I would do is just write down n, and that allows us to calculate b minus a over n, which is the size of the step that we're taking across the x-axis. So you take the big number on your integral minus the small number and just divide by whatever your n value is. That gives us 1. Okay, so that tells us that our step size across the x-axis is 1. And then from there, we can build our table of values. So the way we build this table is going to feel pretty similar to what we did with the trapezoidal rule. You start at A, you finish at B, and you go up by whatever your step size is. We said b minus a over n is 1, so that's going to be our step size. So we just get 1, 2, 3, 4, 5 for our different x values. And then for y, the function that you're plugging into is whatever function you're trying to integrate. So in this case, it's the square root of 1 plus x squared. So what we're doing is we sub into these y values is just figuring out the heights at these different points along the curve. So subbing in here, you would have root 2, root 5, root 10, root 17, and root 26. And I would say it's easy enough just to keep these numbers as roots. I actually feel like it's simpler to do that than to plug in and get decimal versions of these numbers. So the idea is just to figure out y, write it down quickly so that when we actually plug into the formula, we don't have to do too much thinking at that point. And from there, we can think about plugging into Simpson's rule. So Simpson's rule says that the integral that we are trying to compute, the integral from 1 to 5 of the square root of 1 plus x squared is approximately equal to b minus a over 3n times some y values. Now you might just want to write yourself a reminder here for what the coefficient pattern is going to be. The first and last y values always have coefficient 1, and then in the middle they alternate between 4 and 2. So it starts at 4, it goes 4, 2, and your second last one will be a 4. So that's the pattern we're looking for there. And if we do that, then it makes it a little bit easier to write out this expression. So we're going to go y0 plus 4y1 plus 2y2 plus 4y3 plus y4. So in terms of subbing in, I think the thing we have to be most careful of is just this number that's in front of the brackets. This is like saying we want to take 1/3 of whatever our step size is. So let's keep that in mind and let's try plugging in. So our step size was 1. We need to divide that by 3. So 1/3 is what we're going to see out in front. We're going to take our first y value, which was root 2. Then we're going to go 4 times the second one. So 4 root 5 plus double the third one. So 2 root 10 plus 4 times the next one, 4 root 17, plus the last one, root 26. And just as sort of an intuitive check here, the reason why we need this factor of 3 out in front is to balance with the different coefficients that we're seeing inside the brackets here. So 3 just happens to be the correct number so that we're doing a true weighted average. So let's type this into our calculator. We want to get our answer to 2 decimal places, and you can check that it comes out to about 12.76. So that's our first example of using Simpson's rule to approximate the value of an integral. So this will be our last problem, and this is really going to summarize what we said over this video and the previous one. It's going to allow us to compare Simpson's rule with the trapezoidal rule. So what we want to do is approximate this integral here. We want to do that to 2 decimal places. And we're going to do 2 parts. In the first part, we're going to do it using the trapezoidal rule with 4 intervals. And in the second part, we're going to do the same thing, but with Simpson's rule, using the exact same number of intervals. And we want to figure out which rule performs better. So let's jump into part A. First thing I would get into the habit of doing is just writing down what is n, and then from there calculating the step size b minus a over n. So b and a are the numbers on our definite integral. We're going to go 2 minus 0 over 4 to give us 0.5 for our step size. And once we've got that, then we can build our table of values. And we'll be able to use that table of values for both parts of the problem, so we won't have to replicate that work. So you start at A, which is 0, and you go up to B, which is 2, and you're going up by whatever your step size is, which is 0.5. So 0, 0.5, 1, 1.5, and 2. Okay, and then the y values that we're going to plug into come from whatever function we're trying to integrate. So let's scroll back up. Oh yeah, the function we're trying to integrate is this 7 to the x. So y is equal to 7 to the x, and we'll just sub in here to get our y values. So 7 to the 0 is 1, then we'll have 7 to the 0.5, 7 to the 1 is 7, then we'll have 7 to the 1.5, and then 7 squared is 49. So that's probably the simplest way of writing down our y values. And with that, we can jump into our trapezoidal rule. So the trapezoidal rule says whatever integral you're trying to approximate is going to be approximately b minus a over 2n times y0 plus 2y1 plus 2y2 plus 2y3 plus y4. So a couple things I want to highlight about the trapezoidal rule. One, you have this factor of 2 in the denominator. And second thing is that all of these coefficients in the middle of this expression are 2. So you can think of this 2 here as correcting for the different coefficients that we've got going on in the square brackets. So let's make sure we can plug in here. We need to take b minus a over n, which is our step size, and then further divide that by 2. So this is going to look like 0.5 divided by 2. And then in the brackets, our outside numbers are 1 and 49. And then our 3 inside y values are multiplied by 2. So you could say plus 2 times and then give yourself brackets. 7 to the 0.5 plus 7 to the 1.5. And that way you've got something that's fairly easy to type into your calculator. So we want to give our final answer to 2 decimal places, and you can check that it comes out to about 26.58. So we'll store that value away for now. We're going to do a part B where we use Simpson's rule, and then we'll compare which rule gave us the better approximation. So in part B, we're going to approximate the same integral, still to 2 decimal places. Our n value is still 4, but this time we're using Simpson's rule. So first thing I would check is that yes, n is even. That's required in order for Simpson's rule to work. And you would go through the problem in the similar kind of flow as we did for the trapezoidal rule. So you'd write down your n value, you'd figure out your step size. That's still going to be the same as before. So I'll just go over that part again. 2 minus 0 over 4 gives us 0.5 for our step size. And you still build the table of values also in exactly the same way as before. So all of that stuff just recopied from part A. So the difference is that now we're going to be using Simpson's rule. So we're going to say the integral that we're trying to approximate. Formula looks a little different now. It's now b minus a over 3n. So we'll want to be aware of that 3. And then in the square brackets, we have a slightly different pattern for the coefficients. The first and the last y values get coefficient 1. And then in the interior, it alternates 4, 2, and the second last one will be a 4. So if we write this down the way it's written in Simpson's rule, y0 plus 4y1 plus 2y2 plus 4y3 plus y4. So the pattern of the coefficients is important here. And a good intuitive way of thinking about this is that this 3 that we're seeing in the denominator is correcting for the average coefficient that we're using in the brackets. So let's try subbing in. B minus a over n is our step size, and we want to further divide that by 3. So we're going to say 0.5 over 3, and then we're going to take our y values with the correct coefficient. So you take your first y value, which is 1, then you go 4 times your second one, plus 2 times your third one, plus 4 times your fourth one, plus your fifth one. So you can check on your calculator, that comes out to about 24.78. So we've practiced the trapezoidal rule, we've practiced Simpson's rule, and now we're just going to finish off with a little bit of analysis. So for your reference, I'm going to write down what the true value of the integral is. It's about 24.67. So the method for how you get the true value, it's a little bit beyond the scope of this course. It is something that you'll see in your next calculus course. But I'll just say for reference, the true value is about 24.67. So let's compare, what did the trapezoidal rule give us? What did Simpson's rule give us? And which one do we suspect might perform better in general? So Simpson's rule, which we just used, led us to an approximate value of 24.78. And the trapezoidal rule, if we look back on our work from a minute ago, 26.58. So we approximated exactly the same integral. We used exactly the same number of intervals for both, and yet Simpson's rule came out to a much better approximation. So the idea is that in practice, although Simpson's rule is a little bit more complicated because the coefficients are a bit trickier to work with, in general, it gives an approximation that's quite a bit better than the trapezoidal rule. So Simpson's rule is something that I expect that you will see in other courses. So that's all about using Simpson's rule to approximate the value of definite integrals. Thanks for watching.